Hi guys, welcome to the lesson of partial differential equations. So today we are going to discuss some more important methods to solve the heat equation with non-homogeneous boundary conditions. So we know that the heat equation with non-homogeneous boundary conditions, and of course it's a non-homogeneous heat equation. So with the non-homogeneous boundary conditions, or we can say the time-dependent boundary conditions, like this, A of t and U of L comma t is equals to B of t. All right, and U of x comma 0 is some function of x. So now we are going to use the Laplace transforms for solving non-homogeneous heat equations with time-dependent boundary conditions. So this is a powerful method for the heat equation. So let's take an example. So in the earlier example, we solved this problem using the Duhamel's principle and splitting the problem into two parts. So now we are going to use Laplace transform method to solve this equation. So we'll see that how this method works. So the boundary conditions are U of 0 comma t is equals to 1 and U of 1 comma t is equals to t squared, and then U of x comma 0 is equals to 1 plus sine pi x minus x. Now we will apply the transformation to equation number 1. Right, so applying Laplace transforms to equation 1. Therefore, Laplace of ut minus alpha squared, Laplace of uxx is equals to sine 2 pi x plus 2x times the Laplace of t, right? Now the Laplace of ut will be s u minus u of x comma 0, that is the initial condition, minus then the Laplace of this function uxx will be d square u over dx squared is equals to sine 2 pi x plus 2x, and the Laplace transform of t is 1 over s squared, right? So now we can see that su minus this u of x comma 0 is given in the equation. So we can write it from the equation, that is 1 plus sine pi x, 1 plus sine pi x minus x, and then negative alpha squared d squared u over dx squared is equals to sine 2 pi x plus 2x divided by s squared. All right, so we can move this to the right hand side, so we will be left with su minus alpha squared d squared u over dx squared is equals to sine 2 pi x plus 2x over s squared plus 1 plus sine pi x minus x. So now we can see that the heat equation has been converted into a second order differential equation. In fact, it is a non-homogeneous second order differential equation, so we can work out for the two solutions, that is for the homogeneous and the particular solution, right? So we know that u is equals to u homogeneous plus u particular. So first of all, for u homogeneous, we will take this part and we will make the auxiliary equation. So the auxiliary equation here will be as u. So first of all, we will uh, write this equation in the standard form, that is d squared u over dx squared minus su over alpha squared, right? We are dividing the whole equation by negative alpha squared, so again here we will get negative sine 2 pi x plus 2x over s squared alpha squared, and then minus 1 plus sine pi x minus x over alpha squared. Now we can write the auxiliary equation. So auxiliary equation will be r squared minus s over alpha squared is equals to 0. This implies that r is equals to plus minus square root of s over alpha. So the homogeneous solution will be UH is equals to C1 e to the power square root of s over alpha plus C2 e to the power negative square root of s over alpha. So this is the homogeneous solution, right? Now we will search for the particular solution. So for particular solution, we can use the operators D method. We know that it is 1 over d squared minus s over alpha squared times the function, that is this function on the right hand side, negative sine 2 pi x plus 2x divided by s squared alpha squared, and then minus like this. All right, so now we can apply the operator D method, first of all, we will arrange the terms. So we can write in this form 1 over D squared minus S over alpha squared times minus sine 2 pi x over S squared alpha squared, then minus sine phi x over alpha squared minus 2x over S squared alpha squared, and then minus 1 over alpha squared, then plus x over alpha squared. Right, so this implies that 1 over D squared minus S over alpha squared is this. Then now we are writing them separately because we have to solve these elements separately, right? We'll apply the operator D method. So you should be familiar with the operator D method before starting the Laplace transforms, Laplace transform methods for heat equation. And now we can write all these, combine all these terms, right? So we can take the negative sign as common. So it will be D squared minus S over alpha squared times 2x over S squared alpha squared plus 1 over alpha squared minus x over alpha squared, right? This. So now we can solve these two directly. Here what we need to do is we need to put the angle with negative sign in place of D squared. So it will be negative 2 pi x, sorry, not x, only the angle, that is 2 pi whole squared minus S over alpha squared and times negative sine 2 pi x over S squared alpha squared, and then minus, similarly here, negative pi squared minus S over alpha squared sine pi x over alpha squared. All right, so, and for this, now we need to do something different. We will take negative S over alpha square is common. So this will be positive. S over alpha square is common. So in the bracket, we will left with 1 minus alpha squared D squared over S times 2x over S squared alpha squared plus 1 over alpha squared minus x over alpha squared, right? Now this negative and negative, this will be positive, and we can write it in this form: sine 2 pi x divided by 4 pi squared plus s over alpha squared times s squared alpha squared, right? And then this negative negative will be also positive, and we can write sine pi x divided by alpha squared times pi squared plus s over alpha squared, right? And for this, we need to shift this one minus alpha squared d squared over s. So it will be -1 in the power, and this s over alpha squared 2x. And again, I will say that you should be familiar with the operator G method before starting the Laplace transform for this equation, because you can see that in most of the part we are solving the equation by using the operator's D method, right? So this will be, now we can write like this, sine 2 pi x divided by s squared times s plus 4 alpha squared pi squared, right? Plus sine pi x over s plus alpha squared pi squared. And then now this is a binomial expansion. So it's in this way, 1 plus alpha squared d squared over s plus dot 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 like this, right? So this is d squared, and here we can see that this is the highest power of x is 1. So we don't need the terms that are in the series, because the derivative, the second derivative, will make this 0, and the further terms will be also d4 d6 like that, so they will also make this 0, so we don't need them. Only what we need is 1 plus alpha squared d square over s. Still this d square over s will make this whole 0, so we will only left with the function that I will write now. So this is s squared times s plus 4 alpha squared pi squared, right? Plus sine pi x, and I forget to write s over alpha squared here, s plus alpha squared pi squared, and then plus, when this one will multiply with this, we will left with 2x. And now we can write in this way, minus x. No, we don't need to write like this, 2x over s squared over alpha squared, then plus 1 over alpha squared Sorry, this is s squared alpha squared, this one. 1 plus alpha squared minus x over alpha squared, then whole divided by s over alpha squared, right? So now you can see that the function u of x comma s is equals to sine 2 pi x over s square, this one. You can see that sometimes it is very complex problem to handle the Laplace transform, and sometimes it makes the problem very easy to solve. So this will be 2x over s cubed plus 1 over s minus x over s. Now the general solution will be u is equals to c1 e to the power square root of s over alpha squared plus c2 times e to the power negative square root of s over alpha squared, then plus sine 2 pi x over s squared s plus 4 alpha squared pi squared plus sine pi x over s plus alpha squared pi squared plus 2s x over s cubed plus 1 over s minus x over s. Now we will apply the boundary conditions, but first of all, we have to take the transform of the boundary conditions as well. So the Laplace of u of 0 comma t is equals to Laplace of 1. That will be equals to 1 over s, and Laplace of u of 1 comma t is equals to Laplace of t squared. That is equals to 2 over t cubed. Sorry, 2 over s cubed, not t cubed. It's 2 over s cubed, right? Now we can apply the transform, right? So now u of 0 comma s will be equals to, I forgot to write x here. It's my mistake, sorry. In the previous steps, also I think I forgot to write x. Yes, it will be x and x, right? Because we can see that all we are dealing with the function of x here, right? So now we can apply the boundary condition. So u of 0 comma s will be c1 e to the power 0 is 1 plus c2 plus sine 0 is 0 again plus sine 0 is 0 again. This will be 0. This will be 1 over s. This will be 0 equals to 1 over s. This one, right? So this will cancel out. We're left with c1 plus c2 is equals to 0. Now we will apply the second condition, that is u of 1 comma s is equals to c1 e to the power, this will be square root of s over alpha squared plus c2 e to the power negative square root of s over alpha squared, and then plus this is sine 2 pi x. It means that I will put 1, so it will be sine 2 pi, that is 0. So it's 0 plus again sine pi is 0. Then we have 2x over s cube. It means it will be plus 1 over 2 over s cube. And then we have 1 over s, and then plus 1 over s, and then minus x over s, so it will be 1 over s. That will be equals to this boundary condition, 2 over s cubed, right? So this will cancel out, this will cancel out, and we will left with again c1 e to the power this thing plus c2 e to the power this thing is equals to 0. So this is equation number, let's say 1, and this is 2. So if you solve these equations simultaneously, we will get c1 is equals to c2 is equals to 0, because both the so these are the homogeneous system of homogeneous equations, right? So we will get only trivial solution for this system, that is c1 is equals to c2 is equals to 0. So now the solution satisfying the boundary conditions will be u of x comma s is equals to only this part. All right, we're left with only this part. Now c1 and c2 are 0. So this will be sine 2 pi x over sine 2 pi x over s squared into s plus 4 pi squared alpha squared plus sine pi x over, we'll see that what's there. So it's sine pi x over s plus alpha square pi square. Sorry, this is s plus alpha square pi square. And then 2x over s cubed plus 1 over s minus x over s. X cubed plus 1 over s minus x over s. So now we transform the equation from x comma t to x comma s. Now we need to apply the inverse transform to find the function of u x comma t, right? So we need to apply the inverse transform for this function. So we will apply the inverse transform for each element, all right? So it will be easier. Let's say that we are finding the transform of this one. So the inverse transform of sine 2 pi x over s squared into s plus 4 pi squared alpha squared. Here sine 2 pi x, we can take it outside because we need to find the inverse of only the function of s, right? Pi squared alpha squared. Now this is s squared times s plus 4 pi square alpha square. So we need to use the convolution theorem, or we can use the partial fractions to solve this problem. So let's take the partial fraction of this problem. A s plus b over s squared plus c over s plus 4 pi squared alpha squared. So this will be s squared plus 4a pi squared alpha squared plus bs plus 4b pi squared alpha squared plus cs squared is equals to 1. Right, so from here we can see that as squared plus cs squared is equals to 0. And then we can see that from here, so now we can see that the Laplace inverse transform of this function, we can find the inverse transform by using the partial fractions, by breaking the function, because we can not find the transform directly, so we will break the function into partial fractions. So here we did in this step. You can see that 1 over s squared times s plus 4 alpha 4 pi square alpha square is equals to as plus b over s squared plus c over s plus 4 pi square alpha square, right? So by using the partial fractions, we will find a, b, and c respectively, and then we will substitute back in this equation, right? So here we found this is now as squared plus 4as pi square alpha square plus bs plus 4b pi square alpha square plus cs square is equals to 1, right? So by taking LCM, uh, the LCM will cancel with this one here. The LCM will be cancelled and this will be the equation now, right? So we will compare the coefficients to get a, b, and c. So as squared plus bs squared is equals to 0 because there is no coefficient of s squared, so it's 0s squared, and also no coefficient of s, so it's 0s, right? So then 4as pi square alpha square plus bs is equals to 0, therefore then 4b pi square alpha square is equals to 1, right? So this is the constant term, so it will be compared with 1, and from here we will find the value of b, and then we will substitute to find the value of a and c, right, in the equations respectively, in these equations here. So we found a, we found b, and we found c. This is b and this is c, right? So now we can write as plus b over s squared plus c over s plus 4 pi square alpha square in this form, because we have found the partial fractions. We can write it in this form, and then we can easily apply the Laplace inverse transform. So when we this s will cancel with this. When we'll apply the Laplace inverse transform to this one, we will get negative 1 over 16 pi 4 alpha 4, because the Laplace of 1 over s is simply 1. And then here it's s squared, so Laplace of s is 1 over s squared is t, so it will be t over 4 pi square alpha square, and then Laplace of this function will be e raised to the power negative 4 pi square alpha square times t over 16 pi 4 alpha 4, right? So here it is t. Now this will be the inverse transform of that function that was sine 2 pi x over s squared times s plus 4 pi square alpha square. Now we'll find the inverse transform of sine pi x divided by s plus pi squared alpha squared. So again, sine pi x is constant, so we can move it out, and then you will find the Laplace inverse of 1 over s plus pi squared alpha squared. So again, this will be sine pi x times e to the power negative pi squared alpha squared t. Right. So we can call it as equation A, this as equation B. And finally, now we will compute the inverse transform of these three. Now we are done with this one and this one. We are left with these three. So we can find here the Laplace inverse of this function will be x is constant and 2 over s cubed, so its Laplace will be t squared. Then Laplace of this function will be simply 1, and Laplace of this will be negative x. Right, so we can write here it will be xt squared because of this x, right? So we can write xt squared minus x plus 1. Here xt squared minus x plus 1, or we can write it more simplified form, t squared minus 1 times x plus 1. So now the final solution will be sum of all these inverse transforms. So now u of xt is equals to xt squared, or we can write here like this, t squared minus 1 times x plus 1 plus e to the power negative pi squared alpha squared t sine pi x, then plus sine 2 pi x, and the bracket we have negative 1 over 16 pi 4 alpha 4, negative 1 over 16 pi 4 alpha 4, then t over 4 pi square alpha square, then plus e to the power negative 4 pi square alpha square over 16 pi 4 alpha 4. Pi squared alpha square t 16 pi 4 alpha 4. So this is the final answer. Now you can see that you have to be very careful while computing the problem using the Laplace transform, because we are using many mathematical methods that we use the operator D method, we use partial fractions. So we are dealing with a lot of mathematical stuff. So you need to be very, very careful while computing the problem. And we can see that uh, this solution that we got here, we can compare it with the solution that we got from the Duhamel's principle. So they are same, right? We can compare, so you can see this is the solution here. And now will get back to the solution we found using the Duhamel's principle. And here, this is the solution. So we can see that the solution that we found is same as this solution, right? So we can use different various methods to solve the same problem, and even we can use the method of eigenfunction expansion for this problem. So we can use that method too. And now we will talk about some more problems. In the next lesson, we will take some more examples on this topic, right? So we use Laplace transform for solving the heat equation. Thanks for watching the lesson.